A video has recently gone viral on Chinese social media showing a robot attacking a human. It is clear that this machine has the strength and balance to strike an adult male, and without protective gear, the chance of injury would be 100%. That's right, this is the T-800, an advanced powerhouse of a machine from China. While other robots are still struggling just to maintain their balance, the T-800 has already proven its capabilities on the very CEO who created it. But why would they develop such an extreme robot? What is it actually used for? Before we explore the T-800, don't forget to leave a like and subscribe. Stay tuned until the end of the video to find out the real truth behind why the T-800 attacked a human. The year 2025 marked the explosion of a series of super technologies, from robots by Tesla and Boston Dynamics to emerging AI startups. But if you look closely, there is one very clear commonality. They almost exclusively operate in safe, stable, and perfectly controlled environments. In homes, in offices, in spaces where everything has been pre-cleared for them to function. And that is exactly the problem, because the real world doesn't operate that way. Construction sites, rescue zones, or crowded and chaotic environments, these are the places where humans actually need support, yet they are the very places where most current robots simply cannot survive. Consequently, Engine AI's T-800 has emerged as a direct answer to the rest of the equation. They aren't trying to make the robot look friendlier, they aren't sugarcoating how robots will live alongside humans. They chose a more direct and realistic path, building a machine that can withstand force, maintain balance, and control its movements in the most complex environments. They chose a more direct and realistic path, building a machine that can withstand force, maintain balance, and control its movements in the most complex environments. And to achieve this, the T-800 obviously could not be designed as a typical service robot. The first difference lies in the mechanical frame itself. Instead of optimizing for a soft appearance or gentle movements, Engine AI prioritized a structure rigid enough to withstand impacts, but light enough that the robot wouldn't turn into a sluggish block of steel, which is why materials like aerospace-grade aluminum magnesium alloys became critical. This material enables the robot to maintain a weight of only around 75 kilograms, equivalent to that of an adult human, but its structural rigidity is far higher than what any biological body can endure. To put it simply, if a person slips and hits their shoulder on a concrete floor, the result could be a dislocation or a broken bone. For a robot with correctly calculated loads and stress points, that same impact is just another operational scenario within its working limits. However, rigidity alone is not enough, because a machine that is stiff but doesn't know how to distribute force will only end up destroying itself. That is when the drive system becomes the most important part. The T-800's joints are designed to produce a massive amount of torque, around 450 Newton meters, a level of force that no longer belongs to experimental lab robots, but has stepped into a category closer to small-scale industrial machinery. To visualize this, the twisting force is comparable to a luxury sedan accelerating in a high-torque range, meaning that every movement of the robot's legs or hips is not merely lifting and placing, but a process of generating enough power to stabilize the entire body, even in a state of total imbalance. This is particularly vital in environments like construction sites. And it is hard enough for a human to stand on uneven ground. It is even harder for a robot, as even a few centimeters of error in foot placement can instantly shift the entire center of gravity. A weaker robot might choose to walk very slowly to avoid risk, but the T-800 goes the opposite way. It uses the raw power in its joints to pull the body back into balance before a fall actually occurs. It is like a person with an incredibly strong lower body who slips on a step but manages to catch their entire weight and stabilize in a split second. The difficulty here is not just generating massive force, but generating it at exactly the right time. And that is why a robot like the T-800 cannot rely solely on its mechanical parts. It needs a sensor system good enough to see the environment before an impact happens. 360-degree LiDAR and depth cameras are not just features to pad the spec sheet. They are the eyes and ears of the entire system. Through them, the robot can build a real-time spatial model, recognizing elevation changes, moving objects, or even a human arm swinging across its operational zone. In stable environments like homes or offices, this might only help the robot move more smoothly. But in a cluttered space where carts are rushing by, workers are suddenly changing direction, or floors are slippery, it is the boundary between control and chaos. In other words, the T-800's strength only matters when paired with the ability to predict. A powerful kick might grab attention, but what is far more significant is the robot's ability to know exactly when to apply force, when to dampen it, and when to change direction to keep the entire body from toppling. This is what sets Engine AI's philosophy apart. They don't just want to make a strong robot, they want to make a robot that understands force in the real world. And in the real world, force never moves in a simple straight line. Imagine an earthquake rescue zone where the ground is covered in broken bricks, uneven steps, and overlapping obstacles. Humans moving through such a place must constantly use their eyes, reflexes, and experience to guess where the next step should go. For a robot, the problem is many times harder because it has no instinct. Everything must be translated into data, algorithms, and mechanical feedback. That is why the T-800 was not developed as a machine to look pretty on a stage, but as a platform to learn how to survive in uncertainty. I think this is the most notable part of Engine AI's mindset. They don't seem to view the robot as a tech gadget for demonstrating convenience, but as a true physical tool, something that will have to step into places that are much dirtier, more dangerous, and more chaotic than what most demo videos online are showing us. From that perspective, the name T-800 is not just a cinematic reference. It is a very clear statement about the nature of this machine. It was born to handle the most unpleasant parts of the real world. However, this system once encountered a massive wave of skepticism, specifically surrounding a seemingly simple question: whether what appeared in the promotional videos with near-perfect balance and incredibly smooth movements was truly real or merely a product polished by visual effects. The community's reaction leaned almost entirely to one side: too precise to be real, too stable to be a robot. And it was at that exact moment that Engine AI was forced to make a turning point decision, not to persuade with words, but to prove through real-world impact.
Chinese robotics company has released video.
Zhao Tongyang, the CEO of Engine AI, stepped directly into the gym, wearing thick protective gear and standing opposite the T-800 not as an executive, but as a test subject, and then ordered the robot to deliver a full-force strike to his own body, an action he later admitted was not in any risk management textbook. The kick occurred fast, powerfully, and without any sign of holding back, sending him flying off the ground and falling backward in a state of being completely overwhelmed by the impact force. And immediately afterward, while still gasping for air, he stated very clearly to the camera that without the protective equipment, that collision could have absolutely led to broken ribs and internal organ damage, a confirmation intended not to shock but to end the controversy. But what truly made this video a turning point did not lie in the kick. It lay in what happened immediately afterward. The T-800 did not lose its balance, showed no redundant movements to regain its form, and almost instantaneously returned to a state of total stability, as if the system had been designed to absorb and respond to force within the same movement cycle. Something that, in a technical context, means recovery is no longer a secondary feature, but a core part of the system. That exact moment shifted the focus of the discussion, from is the robot real or not, to how this robot learns from such impacts. And that was also when Engine AI began to push this idea further. Instead of viewing collisions as risks to be avoided, they turned them into the most valuable data source. Because in the lab, you can control the force, control the angle, control the environment. But that very control eliminates the most important thing: chaos. That is why the Robot Knockout Legend Tournament was born. With 16 participating teams and a total prize pool of $1.4 million, this is no longer a demonstration stage, but a real competitive environment, where each robot must face unpredictable situations, strikes coming from multiple angles, multiple speeds, and different tactics, forcing the system to continuously adapt instead of repeating what has been programmed. At a technical level, each match becomes a data source that no laboratory could fully replicate. Data on multi-directional impacts, vibrations propagating through the structure, and stress appearing at points that simulations often miss, the things that determine whether a system can survive in the real world. And when humans are brought into this loop through sparring sessions with real fighters like Buakaw, the system learns to respond not just to force, but to unpredictability, where every movement carries intent, where every strike can change in a split second. That is no longer training, that is adaptation. And when every strike is not just a physical impact, but also recorded data, analyzed, and fed back into the system, then the loop begins to form. Deployed to impact, to learn to optimize, to redeploy. Consequently, the only way to validate that philosophy is to take it out into the real world. Not a laboratory, not a demo stage, but environments where everything is unpredictable. In early 2026 in Shenzhen, the T-800 began field testing at busy traffic intersections, places where hundreds of people and vehicles move simultaneously, where humans constantly change direction, stop abruptly, or merge into gaps without any prior signal. This is an environment where most current humanoid robots find it nearly impossible to operate stably. But for the T-800, this is exactly the necessary test. The first point clearly demonstrated is the ability to recover balance. In reality, a robot does not move on a perfect plane. It is constantly subjected to minor impacts, a shoulder bump, a slight push, or simply a misplaced step on an unstable surface. With many other systems, even a minor deviation is enough to force the robot to stop for a reset, but not the T-800. It maintains a state of dynamic balance, where every shift in the center of gravity is processed almost instantly by redistributing force at the joints, adjusting foot placement, and pulling the body back to a stable state. It does not attempt to avoid losing balance. It accepts it and corrects it in real time. The second part is the ability to function in environments with unstable human behavior. At traffic points, the T-800 is used to identify basic violations, such as electric scooter riders not wearing helmets or moving in the wrong lane. But the point is not detecting violations. It is that the robot must operate amidst a flow of people who follow no rigid rules, where every movement is random, and where no two situations are identical. This forces the sensor system and AI to work under noisy, imperfect, and constantly changing data conditions, an environment that a lab can almost never fully simulate. And that is exactly the true goal of this entire process. Not to prove that the robot functions well, but to gather data on how humans and machines interact in the real world. Every minor impact, every shift in the center of gravity, every correct or incorrect prediction. It all becomes data. If the T-800 was previously shown to be designed for withstanding force and controlling movement in chaotic environments, then these tests are proof that the philosophy does not just exist on blueprints. It has begun operating in the real world. Instead of trying to perfect the robot in a controlled environment before releasing it, Engine AI is doing the opposite. They are turning the real world itself into the training ground, an environment where deviation is normal, collisions are unavoidable, and adaptation is mandatory. And if that process continues to repeat, then every deployment is not just usage, but a new lesson. But no matter how powerful or optimized the T-800 is, to move beyond the testing phase and survive in the real world at scale, we still have to return to a very fundamental problem. Economics. Is a price tag of around $20,000 to $25,000 US for a robot like the T-800 actually reasonable? For a security robot, a construction robot, or even an order enforcement robot? Right now, for that same amount of money, you could easily hire a human worker for many months, or even years with higher flexibility, better situational handling, And most importantly, less risk in unpredictable scenarios. Hidden costs that many often overlook. Maintenance, replacement parts, electricity, and the possibility of the system failing in the most critical moments. To put it bluntly, right now, robots are still not the cheaper option. But the notable thing is, China is still deploying them. Instead of waiting for the economics to become perfect, they are doing the opposite, putting robots into cities like Shenzhen right now, where high population density, excellent digital infrastructure, and most importantly scale, turn every deployment into a valuable test. Here, the robot doesn't need to replace humans immediately. It just needs to appear, operate, and most importantly, generate data, establish workflows, and create user habits. At the same time, current pricing is sending a very clear signal about the industry's direction. A robot like the Unitree G1 costs around 16,000 US dollars, but the T-800 is roughly 25,000 US dollars. Compared to humanoid systems in the West, which often have significantly higher development and production costs, and sometimes don't even have a clear commercial price yet, this is a massive gap. It's not because the technology is entirely superior, it's because they are optimizing for something else, the ability to manufacture and lower prices faster. And that is where the Shenzhen cluster becomes a strategic advantage. When the entire supply chain from electronic components, motors, and batteries to mechanical processing is within a range of a few dozen kilometers. Every improvement no longer takes months, but only days. And as the speed of iteration increases, costs will naturally decrease over time. This creates a very familiar loop. From early deployment to data collection, to product optimization, to cost reduction, and finally is wider deployment. From that perspective, robots like the T-800 aren't being brought to market because they are already cheap. They are being brought to market to become cheaper. This is the BYD moment for the robotics industry. It is not the point where the product is perfect. It is the moment a nation chooses to deploy technology while it's still imperfect, in exchange for a long-term advantage in scale, and the speed of innovation. Are you wondering right now, is a powerful robot like the T-800 truly safe? After all, this is a machine that delivered a full-force kick to its own CEOA system that doesn't just know how to move, but is capable of generating enough force to cause injury if it goes out of control. And that is exactly what makes this situation so sensitive. In real-world environments, risks don't necessarily come from major failures, but often start from very minor discrepancies, a noisy sensor signal, a prediction error of a few milliseconds, or a situation that has never appeared in the training data. With weaker systems, those errors might only result in a minor bump. But with a machine capable of force control, like the T-800, those errors can carry clear physical consequences. The next layer of risk lies in the dual-use nature of the technology. A platform that can maintain balance on complex terrain, learn from collisions, and replicate human movement is also a platform that can be adjusted for non-civilian purposes. The ability to climb, react quickly, and maintain stability, the factors that help the robot function in difficult environments, are the same factors that can be utilized in more sensitive scenarios. And once the hardware exists, the boundary between use cases depends primarily on how the system is configured and controlled. Ultimately, the entire system depends on one core factor: data and the learning loop. The more it is deployed, the more data the system collects. The more data there is, the more the AI improves. And as the AI improves, the scope of deployment continues to expand. This is a self-accelerating loop, but it also means the system becomes increasingly complex and harder to predict without clear control standards. Therefore, the answer regarding the safety of the T-800 does not lie in whether it is strong or weak. It lies in how it is controlled. Such a system can only be considered safe when accompanied by clear layers of protection: impact force limits, emergency stop mechanisms, software controls, operational monitoring, and deployment standards in public environments. If those factors are fully established, the robot can operate within acceptable limits. Conversely, if control mechanisms corresponding to the power level the system possesses are lacking, the risk lies not in the technology, but in how it is put to use. The T-800 is not just a machine that is stronger, faster, or smarter. It is a signal that robots have begun to leave the laboratory and enter environments where previously only humans could survive. From construction sites and city streets to unpredictable situations, we are no longer talking about a distant future, but a reality that is gradually taking shape right before our eyes. And as these machines become cheaper, more powerful, and more widely deployed, are we building tools to support humanity? Or are we creating a system that will completely change how society operates? If you want to follow the technologies reshaping the world like this, subscribe to the Massive Tech channel now so you don't miss our next videos.